Hi everyone, welcome back to Chem Story. Today, we're diving into an important part of alkene chemistry, isomerism. We'll take a closer look at cis-trans isomers and EZ isomers. And don't worry, even if it's felt a little confusing before, by the end of this video, it'll all come together. All right then, let's get started. All right, let's start with the simplest type of alkene isomer, structural isomers. These have the same molecular formula, but the atoms are connected in different ways. That difference in bonding is what we call connectivity. For example, with the formula C4H8, we can make 1-butene, 2-butene, or 2-methylpropene. They have the same atoms and the same number of each, but the way those atoms are connected is completely different. And because the structure changes, the properties change too. Now let's move on to the second type, geometric isomers, which are also called stereoisomers. These come up because double bonds can't rotate. Once that double bond is in place, the atoms or groups attached to each carbon are basically locked in position. So if each carbon in the double bond has one group attached, we can describe their positions using the terms cis and trans. If the two groups are on the same side, we call it cis. If they're on opposite sides, it's trans. It's a simple idea, but a really powerful way to describe the three-dimensional shape of the molecule. Let's take a closer look at cis-2-butene and trans-2-butene. In cis-2-butene, both methyl groups are on the same side of the double bond, but in trans-2-butene, they're on opposite sides. Now here's the key point. The double bond contains a pi bond, and that pi bond is what prevents rotation. So you can't just twist the molecule to flip between cis and trans. To make that change, you'd have to break the pi bond, rotate one part of the molecule, and then rebuild the bond, which isn't something that happens under normal conditions. That's why cis and trans isomers are real, stable structures, and they even have different physical properties like boiling point and polarity. Now, the cis-trans system works pretty well, as long as there's one group on each carbon that we can easily compare. But what if there are more than two different groups attached to the double bond? Maybe you've got 3 or even 4 different groups around the double bond, not just hydrogens. In that case, the cis-trans naming just doesn't cut it. It becomes unclear and ambiguous, and that's where the EZ system comes in. EZ gives us a more general and reliable way to describe how the groups are arranged around the double bond. And the best part? It still works, even when all 4 groups are different. So now that we know why we need the EZ system, let's talk about how it works. The EZ system is officially recommended by IUPAC, and the great thing is, it works in a much wider range of cases than cis-trans. Here's the basic idea. Instead of comparing identical groups like we do in cis-trans, the EZ system looks at the 2 groups attached to each carbon of the double bond and assigns priority to each one. Once we know which group has higher priority on each side, we compare their positions. If the 2 high-priority groups are on the same side, it's a Z isomer. If they're on opposite sides, it's an E isomer. Now, how do we figure out which group has higher priority? That's where the Kohn-Ingold-Prelog rules, or CIP rules, come in. These rules help us figure out which group comes first by comparing atomic numbers. Let's make this a little more visual. Take a look at these 2 configurations. In the Z isomer, the 2 high-priority groups are on the same side of the double bond. So you can think of Z as meaning same side. Now in the E isomer, those high-priority groups are on opposite sides. So just remember, E equals opposite side. And keep in mind, it's not about what the groups are, it's about which groups have higher priority and how they're positioned around the double bond. Okay, let's go over the steps to figure out if a double bond is E or Z. Step 1. Identify the 2 groups attached to each carbon of the double bond. Just go one carbon at a time and list what's connected to it. That's it for this step. No need to rank anything yet. We're just figuring out what the 4 groups are around the double bond. Let's try this with a real example. Here's an alkene with a double bond right in the middle. First, look at the left carbon of that double bond. It's bonded to a hydrogen and a methyl group. Now move to the right carbon. This one's connected to 2 larger groups, an isopropyl group and a hydroxymethyl group. All right, now let's move on to step 2, assigning priority. This is where the CIP rules come into play. According to these rules, we start by looking at the atomic number of the atoms that are directly attached to each carbon of the double bond. The rule is simple. The higher the atomic number, the higher the priority it gets. Now, if the two atoms directly attached are the same, we don't stop there. We keep moving outward, one bond at a time, until we find the first point of difference. Let's go ahead and apply the CIP rules to the example we just looked at. We'll start with the left carbon of the double bond. This carbon is bonded to a hydrogen and a methyl group, and a methyl group is just a carbon attached to 3 hydrogens. Now here's what we do. According to the CIP rules, we compare the atoms that are directly attached to the carbon. Hydrogen has an atomic number of 1, and carbon has an atomic number of 6. So it's clear, the methyl group wins. It has the higher atomic number, so it gets higher priority than hydrogen. Now let's take a look at the right carbon of the double bond. This one's a bit trickier. It's bonded to 2 different carbon-containing groups. There's an isopropyl group on top and a hydroxymethyl group on the bottom. At first glance, both of them start with a carbon atom, right? So we've got the same atom with the same atomic number, so at this point, it's a tie. When that happens, the CIP rules tell us to look one step further out. All right, let's take a closer look at what's attached to each of those carbon atoms. First, the isopropyl carbon. It's bonded to 2 other carbons and 1 hydrogen. So we've got carbon, carbon, hydrogen. Now for the hydroxymethyl group, that carbon is bonded to 1 oxygen and 2 hydrogens. So that gives us oxygen, hydrogen, hydrogen. Now all we have to do is compare the highest atomic number in each group. Carbon has atomic number 6, and oxygen is 8. So oxygen takes the lead. That means the Ch.02 group has higher priority than the isopropyl group. Now let's move on to step 3, and this is the final step. All we need to do now is compare where the 2 high priority groups are positioned. Are they on the same side of the double bond? If so, it's a Z isomer. Are they on opposite sides? Then it's an E isomer. In this structure, the 2 highest priority groups, the methyl group on the left and the hydroxymethyl group on the right, are on the same side of the double bond. That means it's a Z alkene. This shows exactly how the EZ system helps us clearly describe the geometry around a double bond. No confusion at all. Figuring out whether a double bond is E or Z is a really common type of exam question. Sometimes you'll get a simple structure, but other times they might give you a larger molecule, like ligemelide B with several double bonds, and ask you to assign E or Z for each one. At first, it might look a little overwhelming, but don't worry. As long as you follow the steps we've already gone through, you'll be able to work through it without too much trouble. You'll see the answer key on the next slide, so I'd recommend giving it a try on your own first. Then check your answers and see how you did. This slide shows all the E and Z configurations for the double bonds in ligemelide B. So when it comes to naming a compound, where do we put the E or Z? We put it right at the beginning of the compound name, just before anything else. For example, if the double bond is between carbon 3 and 4, and it's a Z isomer, we write it as Z 4-ethyl 3-heptene. Now, what if there's more than one double bond? In that case, we list each one with its position and configuration, like this, 2Z, 6Z, 10E. That way, we're clearly showing how every double bond is arranged. No ambiguity at all. And that's it for today's lesson on alkene isomers. We covered structural isomers, cis-trans isomers, and walked through how to use the EZ system step by step. Now you not only know how to identify these isomers, but also how to name them accurately using IUPAC rules. This is definitely going to help when we start looking at more complex reactions with alkenes. Thanks for watching, and I'll see you in the next Chem Story video.